Okay, so next I'll invite the speaker, Miss Namanya, to take the stage. And yeah, let's listen with the open minds and enthusiastic hearts, and we get to learn more together.
Moment, please. I'm trying to share my screen. Okay. So good evening, everyone. I'm hoping it's good evening everywhere. I am Karen Namanya, like they've said. I'm a student at Makerere University, and I work in algebraic geometry, and I'm interested in resolutions and classifications of resolutions and homological algebra and so many other stuff like we will say. So today I'm going to talk about pure braid group presentation. This is something that comes from algebraic geometry, even though this presentation is Coxeter theoretic. I should say that there is as little as possible of algebraic geometry in this talk. So I want to give an introduction. So under the introduction, I'll break this introduction into three parts. I'll talk about some algebra aspects, and I'll talk about topology, and then I'll talk about algebraic geometry. So the algebra. So if you consider a Dinkin diagram, these Dinkin diagrams come from, for example, classification of simple algebras or classification of I groups and stuff like that. So I'm going to consider a Dinkin graph or diagram, AN, that I write as it has n vertices and edges between them. This is n minus 1. This is n. So it has n vertices, and then I'll say straight away, I'll say there is an associated braid group that I'll write as BAN, that is generated by these things I'll call SIs, such that SJSI commute if the ith vertex and the jth vertex are not connected by an edge. So I'll just write this, not connected by an edge. And then there is this sort of relation, SI, SJ, if the vertices are connected by an edge. And then you can think about these SIs as you have string. These things sort of come from braid. So you have this string, and then you can think of SI like the I braid, just going over the I plus 1th braid. So this is I, and then this is I plus 1. So you just have this thing just going over like that. And then the Vi group associated to AN has a Coxeter presentation. Well, I did ask how much time do I have?
You have enough time, I think. You're the only one presenting today.
Okay. So it has a Coxeter presentation that still is as a group, the same generators, S1 up to SI, like S1 up to SN, with the same braid relation, but with an extra relation added. So we have SJ, this commute. if you're not connected by an edge. And then you have this relation. Sorry. If you're connected by an edge, and then you have all the SIs and SJs squared, go to the identity. Okay, so I should note that if you have the AN type thing, this is going to be the symmetric group. This Y group is the symmetric group on n+1 objects. Okay, so in this case, the Y group is just something that we already know what it is. And then I'll say there is a surjective map F from the braid group associated to this Dinkin diagram or Dinkin graph to the Y group. And then we can define the pure braid group so I'll just write like this. PRN is the kernel of F, sorry, because this map goes from the braid group into the Y group, the surjective map. So here we have one definition of what the pure braid group could be. So these pure braid groups sort of appear everywhere. And okay. And then if I go to topology, so I'm going to consider, I'm going to go with an example. You consider the A2 root system. Given by the diagram. So I'll draw a drawer diagram. I'll not draw the real diagram. So by given by this diagram, is x is equal to 0, y is equal to 0, and x plus y is equal to 0. So root systems do really exist. I'm not restricting to A2 roots, AN root systems. They do exist in general for all the different diagrams. And then I'm going to write a few definitions here. I say a hyperplane H is a codimension one subspace of the ambient space. And then a collection of hyperplanes HI is called the hyperplane arrangement. So just write it like this. This is the hyperplane arrangement. And then I can say the chambers of this hyperplane arrangement are the connected components of this unmade space. Sorry. The connected components of the ambient space. I'm just saying V minus the union of all these hyperplanes. I'm going to briefly go back to whatever we've written, and then I'll explain what it is. So if I go back to what we've written, this is a hyperplane arrangement. So we said a hyperplane is a codimensional subspace. So all these lines are dimension 1. The space, this is inside R2. Okay. So the space is R2 and the hyperplanes are all these lines. And this is the hyperplane arrangement, and obviously the chambers are these places, these open simplicial, this sort of open gap in here. Just don't consider the hyperplane. And then we can say a hyperplane arrangement is simplicial if all the hyperplanes meet at the center or at the origin. So in this case, this is still simplicial because all the hyperplanes meet at this point, okay, which is the origin. And then we can say this hyperplane arrangement is Cox star if it arises as a set of reflection hyperplanes of a finite reflection group. And then still this example of ours is still Cox star. And then if you have a simplicial thing, obviously you can complexify. So we are going to say complexifying the hyperplane arrangement. Complexifying, I'm just saying remove these real axes and then replace them with remove these real axes and then replace them with complex ones. Okay, so complexifying the hyperplane arrangement or the real root system in that case, there is an induced group action of a group G. So this G in this case is the symmetric group on the hyperplane arrangement. So it just, the action just permutes the coordinates. And then the pure braid group, in this case, is the fundamental group. This is Cn minus the union of the complexified hyperplane arrangement, hyperplane, sorry. So this is in actual sense equivalent to the fundamental group. Of the ordered configuration. Space of the plane. And we should note that I want to just write some note or remark. But if the hyperplane arrangement is not simplicial, sorry, yes, it's simplicial, but not Cox star, then we can't define, there is no way we can define the pure braid group as that Canol thing. There's no way to define as the kernel of the map F. Okay, because if it is not Cox star, then we won't have this Cox star presentation, and so we won't have a Weyl group that happens. We won't have a Weyl group that happens, and then we can't write that sort of surjective map. And then still as part of introduction, so I go to algebraic geometry. So for example, ， we consider the singularity inside the affine space for. So I'm just going to say the X discrepant resolution and so in algebra terms, what happens is that if you have a singularity, you could resolve this singularity. In this case, we are blowing up a long ideals. You could blow up at a point, you could do normalization, or you could remove a point. It depends on what you're doing. So in this case, we are saying you have discrepant resolution, and then I can put this discrepant resolution in the other hyperplane arrangement that we drew. So I have in here each of these resolutions fits in one of those chambers. Oh God, I'm so poor at drawing. So I have the first resolution I'll write as A, and then I can A1, A2. Okay. Subjection is a problem. So this is 2, 1. Something like that. And then we can say you're putting these discrepant resolutions in each of these chambers. But then there is a statement that says all discrepant resolutions in dimension 3, which we are working in, are derived equivalent. So instead of me having these discrepant resolutions in there, I can draw the same diagram, but in each of these chambers, I'll put like the derived category. I take the derived category. Sorry. Oh, God. Bounded derived category. Sorry. Something like that. And then there are statements that I can draw because this is derived category, so I have factors, but I'm just going to say F2, and then I can say this is F1. I'll explain this what this means in a bit. And this is F2. And then I can say this is F1, F2, F1. So a result by Zenroy. So it's a theorem. Wims, Donovan. There's this, there is that braid relation, sort of a braid relation. It's actually a braid relation. It's equal to F2, composed with F2. And so a group homomorphism. So there exists a group homomorphism G from the pure braid group onto the autoequivalence group on the derived category. Okay, so just write this like this. That. So basically, this work comes from this statement here. So the Wims, who is my supervisor, my PhD supervisor, and Donovan did something. And then they said there is a subgroup of a pure braid group that acts. So this just says that there is a group action on the autoequivalence group of the derived category. So they say that there is a subgroup of the pure braid group that acts on the autoequivalence group on the derived category, but then they didn't have what the presentation was. So my work sort of solved the problem that we give a presentation, what the presentation is, but not all in all cases. And then I'll go to another section now. So I'll begin with notation. So I need J be as connected subgraph of AN. I will explain what connected means. Remember, we said our AN has n vertices. This 1, 2, n minus 1, n. So J is a connected subgraph. What do I mean by a connected subgraph? Connected means that there is no edge in between. No, there is an edge in between two different vertices. So I should be having an edge in between the vertices. And then I will consider what I call the longest element. The longest element, this longest element is in the symmetric group, okay? Because the braid group and the pure braid group are infinite groups. So I'm saying the symmetric group over J, denoted by this curly LJ. And then I can write the longest element on AN as S1. This is a composition of this sort of thing. So Sn. Sorry. So I sort of go up on each vertex and then come down. So this is S2, S1, then I go Sn up to both. But then this definition is not unique because we have braid relations in there. So for example, this part here, this thing, I can write it as S2, S1, S2, because we have a vertex, we have an edge between the first vertex and the second vertex. So I can write this as that. And then I want to give an example. So we have a A2 linking graph, which is like that. The connected subgraph obviously, this is 1, this is 2. Obviously, the singleton, because it is one vertex, I'll just write and shade in. So it is one vertex. So when I shade in the first space, I'm saying it is vertex 1 that I'm talking about, and shade in the second vertex, in the second space, and then obviously the full graph. So if you have a singleton, they are connected, and also this other one. And then the longest element, this is basically equal to S1. This is equal to S2. And then the longest element on the full subgraph is going to be S1, S2, S1, and which is the same as S2, S1, S2, like that. And then the theorem by me is that if you let J be a connected of the AN linking diagram, then the longest element squared, the set of these elements, so you take the longest element and then square, generate the pure braid group. And then part 2 is that there is a new presentation. Okay, so if you talk about presentation, then you need to, if you want to talk about a presentation, then you need to give what the relations are. So here, in this section, we give what the relations are. So I begin by a definition. I and JK be connected subgraphs. Of AN. If I and J intersect, then define distance between I and J as 0. So the distance between I and J is equal to 0. Well, the distance between I and J is defined to be the number of edges between I and J. So I'm going to give the case, I'm trying to form what the relations should be. So the case, I consider the case that the distance between I and J is equal to 2. So they correspond to when I and J are precisely 1 node apart. So I have okay, I have this very many vertices not in there. Doesn't matter. And then this is what I'm saying I, and this is J. So the box here, the box on the left and the right are both I and J, and then this is the node. So how do you know? You can see that the vertices in between, the edges in between there are 2. This is 1, and then this is the second one. Okay, so the distance between I and J is 2, and then you're saying you basically leave one thing in there. So now, given such a pair as this one above, we say that the subgraph is compatible with I and J if K is the connected subgraph of Yasti, because that's the first assumption we make about K. Of the following form. So it's containing the red node. I'm going to draw that just there. So this is the thing we have. So we have So this was our I, this was our J. And then, sorry. So our K can be anything as long as it contains the red knot, and then it is not allowed to start where I start and not allowed to end where J ends. Okay, it should contain the red dot, but it is not allowed to start where I end, start and then end where J ends. And then I can write a proposition very fast. So if we let IJK be as above, we connected that graph. Of AN. So we abuse slight abuse of notation with slight abuse of notation, slight abuse. So we are going to set Li squared. We take the longest element and then square it. It's just going to be I, like that. Then the following relations hold. Furthermore, they suffice to give a presentation. So what are the relations? We are saying I and J, the longest element, squared obviously, commute if the distance is greater or equal to 2. So that means these connected subgraphs are not connected by an edge. This sort of comes from the braid relation. Or I is a subgraph of J, or J is a subgraph of I. Sorry. And then for all I and J, such that the distance between I and J is equal to 2, then I'm taking the longest element. So I multiply I So I'm multiplying the longest element on I squared, the longest element on J squared, like that. And then I'm conjugating by the union of these two. And then still conjugate by the union of J and K. This is equal to, take different directions, sorry, like that. So, and then conjugate by the union. What did I do? IJ, this is IJK. So I should be writing, sorry. I should be writing K dot J dot I, like that. So I conjugate by the union of J union I, and then this is the union of K union J, like that. So this is the thing that we say is palindromic. Obviously, J union K is the same as K union J, something like that. So it takes on the same value. So like like numbers that look the same from left or to right. It doesn't matter. So I want to give an example of how you can look at this presentation here. So we have the relations in place. We have the generators first of all, and then we have the relation. So we have an S3 like that. And then obviously the connected subgraph. So when I feed in, so I'm feeding in the second vertex, and then feeding in the third vertex. These are the singletons, and then I have the doubles. And then the full connected subgraph. And then the longest element. This is S1, this is S2, this is S3, this is S1, S2, S1, this is S2, S3, S1, this is S1, S2, S1, S3, S2, S1. Like that. And then the pure braid group on S3 is going to be generated obviously. We say you take the longest element, you square it, S2 squared, S3 squared, S1, S2 squared, S2, S3, sorry. And then S1 squared. And then I can say this is equal to A, B, C, D, E, and F. So I can say, I'm just trying to nail down my notation, sorry. So generated by A, B, C, D, E, F. We said you have commutativity if the connected subgraphs are far. So first of all, A will commute with C. Okay, so commutes with C. And then, sorry. And then the ones that contain in here. So the first, this S1, this first connected subgraph is contained, this connected subgraph here is inside here. Okay, and is also inside here. So I have A will commute with D. A will commute with F. And then B will commute with D, obviously. And B will commute with F. And then C will commute with E. And C will commute with F. And then D does commit with everything before it, but it also commits with F. And also E commits with F. And then the other relation is that you take connected subgraphs. We say that the notation was, I'll just draw it in a different color here. So I have this, that. So this is my I, this is my J, this is J, I, and then this thing here, the no condition we said I and J should be one node apart, and then K should not begin where I begins and should not end where J begins. So I have a relation here. So I have I, J, and so that means that we have sorry, okay, B, C, and then I'll conjugate by the union, and then conjugate by the union is equal to C, B, A, conjugate by the union, conjugate by the union. So that is one of those examples, the simplest examples where this other relation shows. And then I want to conclude with remarks. So these LIs are motivated by algebraic geometry. Sort of motivated from, let me just draw this diagram. There's this root system that we had from the beginning. So the thing is, you stand in a chosen chamber, which is this one, and then you look at all your hyperplanes, and then you find the shortest path to loop around this hyperplane. So the only way, the shortest path, I would do this, okay? And then this. But if I want to cross this other hyperplane, if I go like this is a longer route, or I can go like that, which is a longer route, okay? But the shortest way I could do this is I go through the center and then come back very fast. And then these are called monodromies around hyperplanes. And these correspond to twist functors in algebraic geometry, which correspond to twist functors. So these generators, these things in the AN case that we've been doing, these are just the Li squared, the things we've been doing. These monodromies are just the Li squared. So these correspond to the twist functors. And like I said at the beginning, Donovan and Wim describe an action of a pure braid group. So they describe an action of a subgroup of a pure braid group. This is the fundamental group that we began with. Without the knowledge of this presentation, without the knowledge of the presentation of the group. So this work basically answers their question. They were wondering what could the presentation be, and then this work gives the presentation. And then other Coxeter types, the Li squared is an analog of An. So if you look at Deakin diagram, for example, I would give an example of D4, which I'm just going to write like this. Okay, so we need to find what the pure braid group is. Okay, with the generators. There is work by Rukia, Raphael Rukia. They say that the generators and others, that the number of generators of the pure braid group is at least the number of hyperplanes for its abelianization. So in this case, we know that if you draw, if you have this D4 thing, this example D4, we know that we have 12 hyperplanes. So here in D4, we have 12 hyperplanes, okay? But our situation, the way we're generating the generators of the pure braid group, we take the connected subgraph, okay? And then we would take the longest element. So I'll just write down the connected subgraph of D4, and then I'll explain what I'm trying to say. This is one. Sorry. The singletons first. And then the double. And then, oh, sorry. And then the triples. And then obviously the full one. So this statement here, Brower, Raphael, and other people say that the number of generators of a pure braid code is at least the number of hyperplanes. We know we have 12 hyperplanes. The only connected subgraphs that we can get are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 connected subgraphs. So if we have 11 connected subgraphs, that means we are missing one other thing that we should square to get the 12 generator of the pure braid group. So that means in this case, our analog of the Li squared does not give a presentation for these other types of the Deakin graph. And then I think that's what I wanted to say.